In this video, we are going to find the general solution to a system of linear differential equations. X prime is equal to x minus y, y prime is 2x minus y, and we're going to solve this using linear algebra by finding eigenvalues of the corresponding matrix of coefficients. So in step one, we want to identify what's the matrix of coefficients for this system, and that would be the top row would be the x prime, so it would be 1, minus 1, 2, minus 1 in the second row. Then we want to find the characteristic equation for this matrix. So we take the determinant of 1 minus lambda minus 1 to minus 1 minus lambda. So we take the determinant of the matrix when we subtract the lambda from the diagonal entries. And so the determinant of this would be the 1 minus lambda times minus 1 minus lambda minus the product of the off-diagonal entries. So that would be minus the minus 1 times 2. And then we can simplify this before we set it equal to 0 and solve. So simplifying this, you can group all of your terms, and what we actually get is lambda squared plus 1. And the eigenvalues are going to be the values of lambda that make the characteristic equation 0. So here we have two complex roots, plus or minus I. And so yeah, once again, we see that we have some complex roots. And we're going to do the same thing with these complex roots as we did when we were looking at second order differential equations. So keep in mind, these characteristic equations, if we have a 2 by 2 matrix, they're going to be quadratic in lambda. So we might get two distinct real roots as we've seen. We might get complex roots. We might get repeated real roots. Whatever the roots are, we're going to generate our solutions, the templates for our solutions for x and y, in the same way that we found solutions for second order differential equations when the roots of the characteristic equation were complex. And so what I mean by that here is, since our roots are plus or minus I in this case, our solution for x, we could write that as some constant times e to the alpha t times cosine beta t. And so our alpha here is 0, so all we get is c1 times cosine of t plus c2 times the sine of t, right? So that looks familiar from our complex roots of characteristic equations before. And for y, we would get c3 cosine of t plus c4 sine of t. And next, we would want to figure out, well, how are these coefficients, say C3 and C4, how are they related to the coefficients in the solution for x? And so one way that you could do this, and this is how the textbook does it, if you've had some linear algebra in the past, you can go ahead and say, find the so-called eigenvectors for each of our eigenvalues. If you don't know how to find eigenvalues, particularly when you have complex roots, then the general method that I've been using is, let's plug these solutions into one of these differential equations and see how the relationships shake out. So for example, I'm going to take my solutions for x and y, and on the next slide, I'm going to plug them into the top equation. Okay, so finishing up this problem, we've got our proposed solutions for x and y, and we're going to plug them into the top differential equation. So x prime would be minus c1 sine of t plus c2 cosine of t, and we're going to set that equal to x minus y. So we've got x is c1 cosine of t plus c2 sine of t, and And then we're going to subtract y, which was c3 cosine of t plus c4 sine of t. And let's group our terms like we've been doing. So I've got all of my sine terms I'm going to circle in blue. And matching up their coefficients, on the left I have a minus c1, and on the right I have a c2, and then I have a minus c4. So from this right away we can see that c4 is actually equal to c1 plus c2. And then we can group our three cosine terms, 1, 2, and 3. And so on the left, the coefficient in front of the cosine is c2. And on the right side, we've got a c1 minus c3. And so from that, we can see that c3 is actually equal to c1 minus c2. So we see how these coefficients depend on both c1 and c2. And now we can plug those back into our original template for the solution for y. So y would be c3, which is c1 minus c2 cosine of t, plus c4, which was c1 plus c2 times the sine of t. And so now we've got our general solution for y down here in red, and we have our general solution for x that we found up top. So that would be our solution to the system of equations.